Right, yes, hello, welcome to WorkerConf here, and I'm honored to give you the first talk. It's about GraalVM, and I will talk about how I can use GraalVM for lightweight microservices in Java. So, we at Oracle Labs, I work at Oracle Labs, and about 8 years ago we started like a little research project. It's really a very long time ago. And we were very ambitious back then, and we were publishing a paper with the title "One VM to Rule Them All." As you can see down in the bottom right here, this research is originating, to a large part, actually from Austria for the local patriots. And so we were thinking about, what about we build a virtual machine that can not just run one language, but that can run many, many languages. And we thought, well, we used the term rule them all to rule all languages. So, and nowadays, like 8 years later, we finally got an open source prototype, but we also got a commercial product, and we got everything around that. But this is like a story that also shows that if you want to do a larger project, sometimes you need 8 years. During these 8 years, we changed also a little bit our marketing because we figured, well, one VM to rule them all, that sounds a little too, too dark. So nowadays we call it GraalVM love them all, and loves all programming languages. And so all programming languages, this is kind of interesting that in the programming language space, there is not a consolidation. It's not like that programming languages get fewer. If anything, they actually get more. And on the right here, I have like a little graphic that illustrates that. It shows basically that from the TOB index, there's many, many programming languages that are popular nowadays. And there's a lot of programming languages that are quite popular that are not even on here on the top 20 list, like Kotlin, for example. So in this scenario, we really wanted to build something that can run everything. And we started off with running JVM-based languages, which means Java, Scala, Groovy, Kotlin. And then later we added other languages to the GraalVM ecosystem, like Ruby, Python, R, and JavaScript as well. We then included static languages like C, C++, R, Rust, YR, that's not R, that's Rust, sorry. We included static languages to kind of also run them via LLVM bitcode. And we then not only run those languages on the OpenJDK platform, but we also run on other platforms, like, for example, on the Node.js platform. So you can run those languages in combination with, on top of the Node.js event loop, for example. We run them via Oracle, so we also run them in Oracle database, of course. Everything needs to be also there. And we also run them standalone. Meaning you can create a small executable from these languages and run them as a standalone, in a standalone way outside of a Java virtual machine or outside of Node.js. There's 2 editions, as I said. There's Community Edition and Enterprise Edition, and you can download and try both. Okay, so that's enough of introduction to GraalVM. I don't want to be too GraalVM specific in this talk, and I want to also give you some things that are kind of more generally applicable. I talked about, my talk is a little bit about performance or maximizing performance on GraalVM. So when people talk about GraalVM, or about performance, when people talk about performance, then they can mean many different things. And usually the main thing people mean when they talk about the performance of a computer program is its peak performance. It means how much performance do you reach after you warm up the program. You run the program for a couple hours, and what's the maximum peak performance you can reach in that time? That's one of the things, but it's certainly not everything people care about. The other dimension that people care about is startup time. It's more like, how does the program fare in the first few seconds, maybe in the first few minutes? Kind of what's the performance of the program at the beginning? There's another dimension that's interesting from a performance perspective. It's the memory footprint of the application. It's how much memory does this application occupy on my operating system? What's the RSS size, the residence set size of the process that is running that application? And as this diagram here suggests, these are multiple dimensions, and as you choose a solution to run your program, you usually make trade-offs. You trade one of these things against another. Apart from memory footprint, another interesting thing can be max latency. That's often interesting for things where you have a web server and you really care about the worst possible response time. That is what this max latency is about. Meaning what's the worst experience a user can get. And in garbage collected languages, where you have a garbage collector that sometimes needs to clean up the heap of the application, there can be spikes in latency, and that can negatively influence your user experience. So max latency is another one of these things that you can trade off against some of the other components. Another dimension is packaging size. When I deploy the application, how much what's the size of the package? And depending whether you deploy a mobile application or you deploy a server application, you might care about packaging size or not at all. So this can be Docker image size or could be the size of your mobile executable. Package size is another one of these things that can be traded against other things, because there are peak performance optimizations that will increase the peak performance, but that increases also your binary size, for example. So there's many more dimensions actually on smaller and smaller details, but these I think are the 5 main things you should think about when you choose how to deploy your application and what's the platform or technology you use to deploy it. And you should really think about basically, do I care about this part or not at all? And then you can kind of modify or have flags on your virtual machine to trade one against the other. So in GraalVM, we have 2 modes of operating. We have one mode where we are running on top of OpenJDK, like a normal Java-based virtual machine. And we have a second mode where we run ahead of time compiled. So this is new for Java developers, because previously Java developers were always running on top of a Java virtual machine. So you always have interpretation going on, and you always have like a big virtual machine behind it. Big, I mean in terms of memory footprint and startup time. What native image gives you for GraalVM is a way how you can create executables that are similar in terms of size and compactness to Go executables. It's a full executable that can run on its own. It does no longer need a virtual machine that is installed. And we give you these 2 modes of operating your Java programs because they allow you to nicely trade off against these 5 principles that I showed on the previous slide. So how do we do this ahead of time compilation? Well, in order to know what type of code to include in that final binary, what we do is we analyze your Java program and check what is reachable from the main method. We analyze sort of all the possibility of code that can be executed. We then use this type of analysis to create a final machine code, fully ahead of time compiled. And this final machine code contains not just the code, it also contains a snapshot of your Java heap at the point after your classes were initialized during the image generation. So you can also use it to have data structures prepared and that are immediately starting up when you are starting that binary. So one of the first trade-offs you take with ahead of time versus just in time, ahead of time versus just in time, is the startup time. A just-in-time compiler, and that includes not just the Java one, that's also the one that's for JavaScript there. A just-in-time compiler system usually goes over various of these steps at program execution time. So when you start your Java program on the JVM, the first thing you do is you load the classes and code from the file system. You verify that the bytecodes are correct, that there is no problems with the bytecodes. You start interpreting the bytecodes, which is very slow. So the typical difference between interpreting something or compiling it to machine code and running it in terms of performance is about 50x. So it's about 50 times faster to run the machine code of a program versus running the interpreter who runs the program. It's like 1 order of magnitude. So you run all the static initializers fairly slow. Then on the JVM, you start a first tier compilation because you have multiple tiers of compilation that get that try to be faster in compiling and then produce better machine code. You're doing this because the interpreter is so slow, so you want to get away from the interpreter as fast as possible. So you don't want to like spend a long time creating a perfect machine code and all the while you're all in interpreter mode. You want that thing a little bit gradual. So on the JVM you get a first compilation, then you gather profiling feedback. Gathering profiling feedback from the application is checking the application's behavior. Profiling feedback includes things like how often was a loop executed. It includes things like what types occurred on a certain place in the program. And the profiling feedback is quite important for the final JIT compilation because it gives you better performance when you know, well, this loop was executed very often, so I should use vector instructions, or this loop was executed almost never, so I should not use vector instructions. So a lot of the decisions in the JIT compilation process are based on that profiling feedback. And then once you got the profiling feedback, then you finally run your second tier compilation, which is the final one, and then you run with your best machine code. But as I already can see here, this is a long time on the JVM until you reach that peak performance. When you run with ahead of time compilation, well, you load the executable and you run with the best machine code. That's simple. So there's a huge difference here in startup time, therefore, between those two approaches. And compilation actually on the JVM can be quite significant for some programs. I have here a little inside data from Java Flight Recorder. Java Flight Recorder is a tool to analyze Java programs. If you're like it's in a very detailed way. And what this tool shows, among other things, it shows how long a compiler thread was running. This is an example workload that compiles the Apache Spark GitHub checkout with the Scala compiler. As you can always see, we're very multi-language today. So this is a Scala compiler running on the JVM, compiling Apache Spark. And it runs for 3 minutes. And what you can see during these 3 minutes on a relatively beefy machine, we have 3 compiler threads. And the yellow here means the compiler thread is busy. It's producing machine code. So during these 3 minutes of compiling here Apache Spark, all we're doing all the time is compiling. We spend a lot of CPU cycles on that. And at the end, when we see some green sections here, when sort of the compiler starts to be less busy, well, the program stops because you're done compiling your Apache Spark. So this is an example of where in a JIT compilation mode, you're spending all your energy on compiling something, and when you're done compiling something, like it doesn't even run because your program is done with what it was supposed to do. So this is just to illustrate that the compilation speed or getting to a faster compile faster is quite important. So our measurements on startup time, and I'm showing here 3 different measurements for 3 different Java microservice frameworks. One is Helidon, the other is Micronaut, and the other is Quarkus. Quarkus is the newest of the 3. Micronaut is about 1 to 1.5 years old. And this shows the startup time when you go with AOT versus JIT. So the speed ups on startup time is about 50x, approximately. And so this is nice because in such a setup, you can almost start a new process per request. Like when you have 16 milliseconds startup time, okay, that's fine. And what it helps you with is you do not need to keep sort of a process idle or anything. And it makes sort of the overall memory consumption of this system a lot smaller, specifically when you don't have always a peak load. So the GraalVM JIT mode here runs on the JVM. GraalVM EOT mode runs with native image. So startup time, of course, EOT is the clear winner. What about memory footprint? So memory footprint is interesting as well. And the interesting thing there is that on a JIT compilation system, and it includes the JVM and includes also JavaScript engines, you need to have a lot of metadata around just to be able to JIT in case something has to be JITted. So this metadata on the Java virtual machine includes the loaded bytecodes, kind of the sources of the program. It includes reflection metadata, like names of variables, etc., that you wouldn't be necessary to execute the program, but they're necessary in case somebody attaches a debugger to the program. You have the code cache. This is where you store your just-in-time compiled code. Also takes memory. And you got the profiling data that is necessary to gather when you want to JIT compile next. So the profiling data, as I said, is counters on loops, counters on branches, etc. And finally, the JIT compiler can also take up data, hopefully only temporarily, only during the compilation process, but still you often have some caches lying around that will permanently affect your memory consumption. In EOT mode, well, you load the application executable, and that's in memory, and you get the application data in memory. Again, here a clear winner in this metric specifically is EOT, because you don't need that metadata around. And we benchmarked the same three Java frameworks in AOT mode versus in JIT mode. And the results are similar to the startup time, a little less impressive, only 5x smaller. And it reduces the memory RSS size. So this is running those services up to the first request. When you run it in JIT mode here, it's about 100 megabytes, 180 megabytes, and in EOT mode, you get down to like 17 megabytes, 41 megabytes of resident set size for the program. I say resident set size because one important thing is the memory of your application is not just the memory on the Java heap. So some Java programmers would say like, oh, I measure memory, I measure how much memory is on the Java heap. But that's not accurate because there's only a part of the memory is the actual Java heap memory. A large part of the memory is outside of the heap. All of these profiling data structures, etc., are not part of the heap. And also, it can be misleading to generally use the heap usage as a memory consumption metric, because for memory consumption, what you're interested in is how much of the memory is actually currently swapped in by the operating system. So you want to measure the resident set size of the memory. Measuring that resident set size is tricky because it depends on many factors and heuristics in the operating system. So even if your application does always the same thing, the resident set size might go up and down. Therefore, we recommend to measure the resident set size of an application over time and look at the final graph. In the end, so here is a graph of resident set size. That's the blue line is the real memory used by the application. And in the end, what you're interested in is sort of the area under the curve for your application. So this shows resident set size during the first 10 seconds of this web server application when run in GraalVM JIT mode. And it also shows the CPU usage, which is the red lines. And in the JIT mode here, the startup is about 800 milliseconds, and the resident size about 350 megabytes. And then in the EOT mode, we see this goes down. The startup is only 8 milliseconds, and resident size only 13 megabyte. You see here 13, like between 12 and 14. But what's also very interesting is that we use like significantly less CPU time. Because in the JIT mode, what's happening is that during the startup of the app, like a lot of compilation happens. So most of the CPU usage you pay here is actually for the compilation, not for your application. And similarly here, actually, on the second request, suddenly we get another spike, because maybe another part of your program got hot, and then you get another spike of your CPU usage. That can be interesting when you like run many different processes on the same server. They will compete for the CPU resources, and therefore Therefore, here the EOT mode is using a lot less. This tool, by the way, is I think highly underrated. It's called PS Record. It is a tool that allows you to it's a Python tool that allows you to draw these curves of resident set size over time for any process. So that was on startup time and memory footprint. Let's talk about peak performance. And for this, I have a little quiz first. I have here 3 Java programs to negate a number. And the first one here on top is negate 1. The second one is negate 2. The third is negate 3. Well, actually, we can make this a little bit more familiar to JavaScript programmers nowadays. This actually compiles with the latest Java version. If you're not following that space, but you got the var keyword now also in Java. But anyway, so this is 3 programs, and they will look very similar in JavaScript, and the answer is going to be similar as well. So the question is, which of these programs runs the fastest? The last one runs the fastest. All right, let's make show of hands. Who thinks the first one runs the Okay. Who thinks the second one runs the largest? Fastest? The third one? Okay. All right, and the others don't show hands because it's a trick question. That's right. Yes, exactly. Well, you got me. It's a trick question, and like in the final machine code on most modern JIT compilers, they should run equally well. Meaning it should not matter which of those 3 you write. And like here it's relatively clear because it's just a local variable, so it goes away. The JIT compiler will never like produce code for that. It will be able to, and it will be able to do these A+0 thingies, right? You might think like, I would never write stupid code like that, right? I would never write A+0. Why does the JIT compiler even care about that? Has the optimization in there? The reason is the JIT compiler does a lot of inlining, and if you're a good programmer, you will do a lot of helper functions, or you will try to abstract things. And then in the end, when the JIT compiler does the inlining, this type of constructs appear quite often. So it's actually the sign of a good program if the JIT compiler finds these constructs in your final graph. It's a sign of a bad program if it finds it in the initial graph. Okay. But yeah. So the last one is a little bit more tricky because in the last one you have some object allocations and some boxings. You turn values into objects. This last one on a modern JIT compiler still works very well because modern JIT compilers have escape analysis, so they can remove object allocations. They can figure out that this object actually doesn't need to be created because only one thread can see it. The last example, however, if you use a not so modern JIT compiler, like for example the client compiler in Java, the last one will run slower. So there's quite some compilers where the last one will run slowest. But the first 2, almost every compiler would run at the same speed. One interesting part to amend this little trick question is what happens in this scenario here. So because, look, I mean, we are creating here this stupid object, so we are, of course, doing some caching, right? Caching makes things faster, I heard, right? So, so we are caching stuff, right? Who thinks this runs faster? Nobody. Who thinks this runs the same speed? Nobody. All right. Well, almost nobody. Well, at some point, yes. So it actually depends. If you got a very, very good virtual machine, maybe in the future this will run the same speed. On current virtual machines, this runs slower because it will run faster if the compiler doesn't do escape analysis. So if you run with the client compiler only, or if you run interpreter only, this will run faster. But if you run with a good compiler, like this will run a lot slower because the compiler can no longer prove that it doesn't need to allocate this object. And then the object location is there, and then suddenly your performance drops, right? So anyway, so the bottom line is write abstract code, write small helper methods, because all of this stuff the compiler will do for you. Do not do small-scale compiler optimizations like removing the usage of a local variable or something, because none of this will matter. And avoid caching, like try to create objects locally and have local computation, because those will be optimized best on modern JIT compilers. Okay, cool. So performance generally, and peak performance as well. Performance is hard to measure. I have here a little graph, which is from our internal tool, how we measure performance. We literally have like thousands of these graphs internally on various benchmarks and metrics. And this is a dot for every check-in we do. For every check-in, we run the test. And we did a lot of work trying to stabilize this workload, but it never goes. Like the workload is actually running for quite some time and tries to figure out the final peak performance. And these are the results of the final peak performance. Now you can see the results go up and down all the time. And that's not because we are changing the code base so frequently. So what's happening is that sometimes a program can have sort of these two states. Because during the initial phase of profiling information gathering, there is some uncertainties because it's not thread safe the way VMs and Java VMs, for example, gather the profiles. So it depends on external factors. So depending whether you're lucky or unlucky on your profile, you get either this performance or that. And you're basically alternating between the two. And this is like zoomed out over like 1.5 years. It's a little bit hard to see on the screen, but like, yeah, we see like, well, we get a little bit better over time, but it's just to show you like how hard it is to actually get an actual performance measure. Always when you measure performance, make sure your measurements are repeatable. Like if you do a one-time measurements of a performance on a normal machine, like it says nothing. Because there's not just the program and virtual machine, also the hardware layer has so many uncertainties and so many things that are kind of, yeah, that can vary from run to run, that like you need to have a lot of repeatable runs. So always repeat the runs and give like an error bar when measuring performance. So on throughput, on the max throughput, meaning the maximum achievable performance of the application, the GraalVM EOT mode is worse than the GraalVM JIT mode. That is because in the EOT mode, we are missing profiling feedback. We are missing kind of the information that is given to the JIT compiler to create a better program. You can see here we have here a couple of web requests, and up to about 100,000 requests, the EOT mode is still faster. But then from 100,000 requests onwards, the JIT mode starts to take over. It's when everything is warmed up, everything is in stable state, you're good to go, you have a better throughput on the JIT mode. We are trying to reduce this advantage of the JIT mode with profile-guided optimizations that they can also do offline. What you do there is that you create a binary of native image that is instrumented, and this binary can be used to run relevant workloads and create an iProf file which contains the profile, and that profile is fed back into another image generation run to create the optimal binary. This setup, by the way, allows you also to be more stable in your results because you can fix your profile. You're no longer dependent on what happens during the startup of the application, but you can determine on what data you want to train your application to be fast. It's like a little bit like machine learning. You train your application on certain workloads to get like a certain profile and use then the profile as the decision tree for the RT compiler. With this PGO, we are actually making up a little bit for this difference in terms of the peak performance. There is still some minor differences that are, however, now mostly application specific. But generally, with profile-guided optimizations on EOT, you can get also on peak performance to a similar setup as the JIT compiler. So to summarize, well, the JIT has a better time profiling at startup. It can make optimistic assumptions about things because it can recompile if it wants to. So this is another advantage for the JIT. And the EOT needs to handle all cases in machine code ahead of time, which can also be a problem if you don't know your target platform. Also, that's relatively rare nowadays. Nowadays, people often know, like, I want to deploy into this cloud, or I want to deploy into this iOS system. So it becomes rarer nowadays because the hardware actually becomes less diverse. We have practically only two major ISAs nowadays with ARM and Intel. But this is another thing to think about. You need to fix yourself to certain machine code. And for example, you need to fix yourself, do I want AVX instructions or not? And then I can no longer run on an older Intel. Profile-guided optimizations help EOT to achieve peak performance, and you get a predictable performance, which is actually an advantage of EOT. Talking about benchmarks, well, we need more benchmarks. Always more benchmarks is better. Because optimizing for few benchmarks is like overfitting a machine learning algorithm. It's like if we as compiler constructors optimize for too few benchmarks, the compiler has a lot of heuristics that try to do approximations on whether to apply an optimization or not. If you run on too few benchmarks, we will tune those heuristics in a way that they will overfit on those benchmarks. Meaning those benchmarks will run very well, but if you give it an arbitrary program, it will be really bad. So that's why we believe that more benchmarks is better, and that's why we as the GraalVM team try to run a lot of different workloads, rather than focus on a few and make them very good. And one of the things we started there is the Renaissance.dev website that gathers benchmarks for JVM-based languages, Java and Scala, including Apache Spark. Generally, all benchmark data is useful, but be careful with conclusions, specifically around benchmark data from a single run, or benchmark data that's not that reproducible. Often people, when they run a benchmark, they might not actually measure what they think they measure. They might think they measure peak performance, but in effect they measure warm-up time. So there's a lot of pitfalls that are possible when doing the benchmarking. But yeah, so we think more benchmarks is better. We got you a couple of benchmarks on that website. Packaging size. That's another metric that can be of interest. It depends again on your scenario. It's pretty interesting for mobile applications. There is tools from Facebook, Google, etc. to actually try to make them as small and compact as possible. Because on your mobile app, in your app store, if you have to download 150 megabytes on some areas, this is like reducing your user count. In the cloud, it can be interesting for your Docker images to be smaller. But it's probably not such a big concern. It's always a concern when you want to distribute your binary to users. So in the JIT compilation mode, you will get larger distribution sizes because you also need to distribute the Java virtual machine. Maybe that's already installed on your system, then you're kind of good. But often you need to package everything together in a Docker image. And then you need for a Docker image also like a lightweight operating system underneath, like Alpine Linux. The JIT compiler can load the code on demand. This is an advantage in packaging because you don't, sometimes you would evaluate another piece of code and you don't exactly want to know all the code at packaging time. Whereas the EOT compiler needs to know all the code that you're running at image generation time. In EOT, everything is a single binary, which means you have a smaller constant overhead. You don't ship a full Java virtual machine, you only ship your binary. And the binaries can be 6, 7 megabytes for smaller programs. They can run on a bare metal Docker container. There's actually a flag, -- static, that allows you to create a binary image that has everything linked in to run on an absolute bare metal Docker container. And so they have a smaller constant overhead. They do have limited support for reflection and GNI and resource management, because in our EOT compiled code, we need to know at image generation time all reachable paths of the program. So it's harder for the JIT compiler to support arbitrary reflection or arbitrary evaluation of code at runtime. To summarize, this was the graphic I showed you at the beginning on the type of metrics you can be interested in. Startup time, peak throughput, memory footprint, max latency, and packaging size. When on this diagram we plot the JIT mode of GraalVM, then we get approximately this. So the peak throughput is very good, max latency is very good because you have all the garbage collection options from the Java virtual machine available, including concurrent garbage collectors, etc. What is not so good is the startup time, the memory footprint, and the packaging size. When you run in the EOT mode of GraalVM, the picture is almost the opposite, meaning you're really good on startup time, you're really good on memory footprint, and you're really good on packaging size. These are the three metrics where EOT mode is a lot better than the SID mode. But you're worse on the peak throughput, if that's what you care about. And you're at the moment worse also on max latency because the garbage collection options are not that big when you run on a native image. So on the peak throughput question, yes, you get less peak throughput, but maybe on a scalable application, what you care about is throughput per memory, meaning how much throughput do I get if I use a certain amount of memory, and then actually the EOT mode might get in front again. And that's generally like an area where we're currently working on a little bit more, like we want to eat the cake and have it, of course. So how can we mitigate the downsides of the ahead of time compiled mode? One is, I already mentioned in the presentation, it's improved peak performance with profile guided optimizations. This helps with the peak aspect. What we're working on as well is low latency garbage collection options. So, because that's more an implementation detail of GraalVM than a kind of a high level difference between EOT and JIT. There should be just the same garbage collections available. And the final downside that we try to mitigate is to simplify the configuration and deployment time. So to simplify how you can, because at the moment if you have a very complex Java application, you might not be able to run the EOT compiler on it because it uses too much reflection or too weird constructs. Therefore, at the moment, when you are running with GraalVM EOT, we recommend to use one of these three web frameworks that are targeting GraalVM EOT as one of the backends. First one is Micronaut. It's a new Java framework. Second one here is Helidon, and third one is Quarkus, a new one from Red Hat. Probably Quarkus has the best support for GraalVM at the moment because it was built from the ground for GraalVM. Yes, and so with GraalVM EOT for JVM-based applications, we hope to make a difference in the server space moving forward for Java applications in areas where the memory footprint and startup time of the JVM was a problem. And we got quite some support also from competitors. Here I quote the Microsoft Azure advocate, Bruno Borges. Before you think about porting Java code to Golang, I strongly suggest you to evaluate GraalVM substrate VM native image option. So this is because with substrate VM and GraalVM native image, you get effectively this very similar performance characteristics in terms of startup time and memory footprint and packaging to a Go binary. You can think of it as something like, it's the type of packaging you get for Go but for Java. And not just Java, but also Scala, Kotlin, or other JVM-based languages. GraalVM can do more. Last year, I showed kind of the multilingual aspect. This is here a little fun program running Node.js with Java interoperability and then reaching out to R for statistical computations. You can do all of this in the same program. This is interesting kind of if you want to have, you have a Java app, but you still want to use Node.js on the side, then you can use GraalVM for that. We have in GraalVM a fully compliant ECMAScript compliant JavaScript virtual machine, and yeah, it can run all of Node.js. So this type of program gives you an output like this, where you use big integer from Java, and then you can get the plot from R, for example. But specifically Java and JavaScript is something people like to combine a lot. Another interesting thing here more for JavaScript developers is Vertex. So this is Red Hat Vertex core developer, Paulo Lopez, recently started a new project they call ES4X, where they run Vertex with GraalVM as the way to run JavaScript. And you get basically all of the new JavaScript features when you run in your Vertex environment. GraalVM is a multiplicative value add ecosystem. So it runs a lot of different languages. It uses the same optimizations, tooling, interoperability, and security features for these languages. And then it can run those in multiple embeddings. That includes Hotspot JVM, Oracle RDBMS, Node.js, and others, including standalone. And we really see this as an ecosystem, and we want to invite people to join that ecosystem. Because if you implement your own language on top of GraalVM, if you implement your own tooling with GraalVM, then it will work across these languages. So this talk was focused on JIT versus EOT on GraalVM for JVM-based languages, but the long-term story for GraalVM still is a polyglot story. It's about supporting all these languages and supporting them to work together well. And in this story, we certainly invite people to become part by adding their own language, adding their own embedding, so use GraalVM as a way to run other languages, or to add their own language agnostic tools. We are a big open source project on GitHub. You can find us on GitHub, github.com, Oracle Graal. You find us on graalvm.org that has a description of what we're doing. And yeah, please join us. Please join us in terms of also on Twitter, GraalVM handle, and help us, give us feedback there. Thank you very much for your attention. I'm at the end of my talk. I'm happy to answer questions. Thank you.
Okay, thanks a lot, Thomas. Are there any questions?
Hi, this was really interesting, this performance chart or diagram. I just wanted to ask a question. So if you want to run JavaScript but also have some Java, then this looks really like it makes sense. But what you talked about with JIT versus AOT, and what Benedict does with V8 is they have both JIT and AOT. Do you know how do these things compare when you only have JavaScript code?
Yes, so at the moment this JIT versus EOT for GraalVM only applies to JVM-based languages. It does not apply to JavaScript. So if you combine JavaScript and Java, you can EOT your Java code, but you cannot EOT your JavaScript code. We are working on that. So it is something we will do in the future as well, to EOT the JavaScript code after you warm it up. So the EOT that V8 does, I was talking with Benedict yesterday, is it is storing the bytecode, so you don't need to parse them again. But it would then interpret the bytecodes. What we will try to do with JavaScript, so it will still have to compile them, right? Yeah. What we will try to do with JavaScript, I don't know whether it will be successful or not, is to also store the machine code, which will mean that for a specific JavaScript web tool, you might be able to not just deploy to your user your JavaScript code, but already the final machine code as well. I mean, typical tools would be NPM or something. So we are working on that. It's currently not the case that this works, but it's something we're researching, and you can expect something from us over the next couple months on that. Thanks for your question.
Any other question? Yeah.
So my question is, would it also be possible to use the AOT compilation for a rather complex Spring application where a lot of reflection would go on?
Mm-hmm.
And another question, what is the difference of those web frameworks that you mentioned to, for example, a Spring application?
Yes, thanks for the question. Yes, so is it possible to run Spring? At the moment, it is possible to run Spring Foo, which is a side project, which is not the main Spring project. It is using parts of the Spring framework, but it's not using Spring Boot. So Spring Foo examples do work. Sebastian has, the Spring developer, Sebastian has done a lot of work there. We are currently not able to run a full Spring Boot application, but we are working with Pivotal to make that happen. So it's very interesting for us to make Spring work, and we are in talks with Pivotal to do a joint effort on that. They were actually announcing on their last Spring conference that the next version 5.3 or 5.2 will have GraalVM support. So we are fixing that. The difference between, for example, Micronaut and Spring is that Micronaut does the dependency injection annotation-based at build time. So Micronaut already does a lot of things at build time and creates Java bytecodes from that. And this reduces the amount of reflection that's in those programs. Spring does not do that. So Spring uses a lot of reflection. But it's not like we do support reflection in native image. It's not like we don't support it. We just need a configuration. So what we're working with the Spring developers is that they will make small adjustments maybe to their framework, but also that they will generate automatically this reflection configuration. One of the tools that we developed in that area recently that will help us that is the tracing agent, where you can run an arbitrary Java program on the JVM, and it will give you a trace of all of the reflection usage, all of the GNI usage, all of the resource usage. And you can use this as an initial configuration. Depending on your test coverage, it might be good enough. But yeah, it is a problem with using runtime reflection, and we are working on that. So we expect that the next version of Spring will have GraalVM native image support.
Okay, thanks.
Pardon? I can hear it.
Same story.
Aspect J. Yeah, probably the same story. Yes. What you should try to do when you have a complex program to run it first through the reflection tracing agent. This should give you a very good hint on. It's actually interesting anyway. It's very interesting the output to see what goes on behind the scenes in these frameworks. Usually you can make these frameworks work. We are constantly like making it easier and easier to configure. Yeah, I mean, one reason why it's so hard is that like originally, like native image is kind of a little bit of an accident in the sense that originally we didn't think that this would be a feature we would ship to users. We thought this is a feature which would only compile our compiler when we link it with Hotspot or rthinger. So it was originally designed to run our code. And when we pushed it out last year, like suddenly, like a lot of people were suddenly very excited about that, and they're like, oh, we want to run everything. And so that's a little bit behind the curve of like what people want to run versus what you can run, but we are constantly improving. So if you have something like Aspect J, for example, yeah, I mean, run the reflection tracing agent. It should give you already the configuration. And also feel free to open GitHub issues for us. Just inform us about things or like what you found about it. Thank you.
Okay, thanks a lot, Thomas. Thanks a lot for your questions.